So we're going to now start something completely new, and that is we're going to look at clusters and we're going to look at metal-metal bonding and isolobal theory, which is a very important, very conceptual and powerful theory in chemistry. And it's a beautiful theory that enables one to do all sorts of wonderful things. All right, so but before we get there, I want us to quickly have a look at clusters. And, well, clusters are an important class of compounds in inorganic chemistry. They're basically compounds, molecular compounds that bear metal-metal bonds. So you have all sorts of clusters, right? And they can be ranked in terms of how many metal-metal bonds you have. That's basically what it is. Now, these are important, and there was a lot of chemistry being done in the 1960s and 70s. The reason was that they thought it's sort of like a link between how the metals aggregate in the actual, or how the metal atoms aggregate in the metal phase, in the solid phase, and the mononuclear case, so the molecular case. So it's somewhere in between, and they thought this could be useful to try and simulate surface phenomena and stuff like that. So that's why these are important compounds. And actually my former supervisor at the University of Cape Town, he was really into clusters. He was a cluster chemist. So, but this is sort of something that was really done in the 1960s and 70s. It sort of reached its high point. There's still people working in it, but it was sort of the fashion back then to investigate these things. Now there's two types of them. We have organometallic clusters. These are basically low oxidation state metals, generally bearing carbonyl or phosphine ligands, neutral ligands. And we have inorganic clusters, which are high oxidation state clusters, typically bearing halide supporting ligands. But all these clusters bear metal-metal bonds. That's the key. Now you can think of these guys here that we've actually encountered before as mononuclear clusters. You can think of this as a cluster of one atom. So in terms of nuclearity, when I talk about nuclearity, I'm talking about how many metal atoms there are. So these are mononuclear clusters that you've seen before, carbonyls. But of course, we're interested in metal-metal bonds. So this is an example. Here are two examples of dinuclear carbonyl clusters. So these are organometallic clusters. Good morning. And so this is dimanganese dodecacarbonyl, and this is the structure. The rhenium analog also exists. It's got a very interesting structure. It's essentially two octahedra which are fused together with this metal-metal rhenium-rhenium bond. And you can see it is somehow eclipsed, the structure. So that's a dinuclear cluster, because there's two metal atoms that have a metal-metal bond. Now I want to quickly, at this point, just sort of digress, if I may, and talk a little bit about metal-metal multiple bonding, which is a very interesting thing. Of course, like with organic compounds, you can have double and triple bonds. But with metals, you can even have quadruple, so a fourfold bond, like we see here, or a quintuple bond, which is a fivefold bond. It's very interesting. So this comes from 1964. This is F. Albert Cotton. This is the first example of a complex featuring a fourfold bonding interaction. So here it's between two rhenium-3 centers. This is a dianion, that's the structure. You can see it's got an eclipsed configuration. And yes, it bears a fourfold bonding interaction between these two metal atoms. So this is also an example of a dinuclear cluster, a cluster of nuclearity 2. It's not an organometallic cluster, it's an inorganic cluster because it has a higher oxidation state. So there's this distinction, remember the slide I showed earlier. Now what you see on the right here is the molecular orbital diagram, the molecular orbital interaction between these two metal centers. So what we have, if you do the electron counts, is two rhenium-3 centers. So that's D4, right? And it's actually very simple. So what we're looking at here is the bonding interaction between these two centers. So we've got, these are the 5 d electrons on each rhenium center. You can imagine having a low-lying sigma orbital slightly higher lying pi interaction. In fact, you can have 2 pi interactions. And in principle, you can have 2 so-called delta interactions. I'll show you what that looks like in a minute. So so what you have in this compound is you have a sigma, 2 pi bonds, and 1 delta bond. Right? So if you count the electrons here, there's 8, and that's why it's a 4-fold bond. Now, what does this actually look like? This is what it looks like. This is the sigma bond, so it's basically this bond at the bottom here, which is very stable. The sigma bond is formed between 2 dz squared orbitals, which form clearly a sigma bond. There's 2 pi bonds, which you see here, sideways bonds. Very, exactly the same thing as what you have with p orbitals in organic chemistry, right? It's exactly the same thing. These bonds are clearly of pi symmetry. And this is what a delta bond looks like. Right, so that's something you definitely haven't seen before. Have a look at how those 2 d orbitals are overlapping with each other. All orbitals are interacting with each other, but from the side. Do you see that? Right, so that's a delta bond. Now, as I said, in principle, it's possible to have a 5-fold bond between 2 metal atoms. In other words, if you look at this molecular orbital diagram here, there is another set of d orbitals that can form principally a second delta bond. And that's actually been done. That's been done very recently, well, okay, not that recently, 2005 by a guy called Phil Power. So this is an example of a dinuclear compound bearing a chromium-chromium 5-fold bonding interaction. This is not so important. This is the distribution of the molecular orbitals between the 2 chromium-1 centers. So this is formerly chromium-1, right? Very reactive compound. Very reactive compound. I made it once myself. It's very reactive. It's damn difficult chemistry, this. And you can see here, what do you notice about this molecule? What does it have around, attached to the chromium? Yes, very big groups. These groups are called metaterphenyls. And they're traditionally used for steric protection, kinetic steric protection, which is exactly what we see here. So these R groups, in fact, are isopropyl groups, but you have all sorts of variations. Now, the guy that made this Phil Power is a guy from the University of California at Davis. Did this starting from the chromium-2 compound. So he started with the chromium with this big group here with the chlorine, and then he did a reduction. And he got this compound. Very difficult chemistry. But anyway, it's a 5-fold bond. And this is the distribution of the in the molecular orbital diagram. In fact, this comes from calculations, right? So they calculated the distribution of the orbitals. And you can actually see the pi orbitals in this case are lower in energy than the sigma. But you can see if you count the electrons, you have 10 electrons. So it's 1 sigma, 2 pi, and 2 delta. So basically what we have here with 1 extra delta bond. So that's very interesting. And yeah. So that was just to digress a little bit, just to show you that you do have this notion of metal-metal multiple bonds, and there's many, many other examples. You also have triple bonds, double bonds between metals, all sorts of interesting things. In fact, I wanted to devote a lecture to that, but we're not going to have time. All right, so that's nuclearity. That's nuclearity 2. We've looked at some examples. We have metal-metal multiple bonds. And yeah, this is nuclearity 3. So here we've got 3 metals. Now these are classic examples. This is triosmium dodecacarbonyl. All right? OS3CO12, that is the synthesis. We start from osmium tetroxide, carbon monoxide, and you get this. This is a beautiful crystalline orange compound. It's very stable. It's not air sensitive. And in fact, to make these clusters, you typically require an autoclave and very high pressures, high temperatures. you know, it's not something that you can just make in a Schlenk tube at ambient conditions. Anyway, this is the structure. You can see we have a triangular arrangement of osmium atoms bearing these metal-metal bonds. You can also have a cluster that has 4 metal centers. So here we have an example of a RH4CO12, right? So this is also a classic example of rhodium carbonyl cluster. The thing with these clusters is it's difficult to predict if the carbonyl groups are going to be bridging or if they're going to be terminal, right? One can't predict that beforehand. You'll notice here all the carbonyl groups are terminal carbonyl groups, whereas in this rhodium center complex here we have some bridging carbonyls. You can see a couple there. Here are some examples of, let's say, higher nuclearity clusters. This is OS5CO16. You can see you have a trigonal bipyramidal arrangement of metal atoms. These are osmium. The greens are osmium with carbonyls. One of these osmium centers, in fact, has 4 carbonyl ligands attached to it. The others all 3. And on the right, we have an example of an inorganic molybdenum cluster. So this has got 6 molybdenum atoms. Look at that. The turquoise atoms, and surrounded with chlorides. So you can see how this goes. You can get lots of metals to bond together, and you can even make clusters like this. This is a borane cluster, and we'll discuss this a little bit today, but this has got 12 boron centers. And in this example here, we in fact have a palladium cluster with 21 palladium atoms. Now, the important thing, guys, is that these are actual molecules, right? This belongs in the realm of molecular inorganic chemistry. This isn't solid-state chemistry. Don't confuse this all with the structure of solids, like salts and stuff like that. This is something different. These are molecular entities. They're very big molecular entities. Now, look at this thing over here. I mean, it's got 21 palladium atoms, and it's got some phosphines and so on. I mean, it's got an enormous molecular weight. And you can clearly see in this example that this is now starting to somehow resemble potentially the structure of palladium as a metal. Yeah? Okay. This is a very nice example of a ruthenium cluster, and it's a nice example because it features right in the center of this cage, of this octahedral ruthenium cage, a naked carbon atom. And that we call a carbide. So we've looked at carbenes, we've looked at carbines. This is a carbide, I-D-E. I should write that down. Carbide, like Union Carbide, the company. All right. And it's essentially, you can think of this as a sort of a naked carbon atom in a molecule. Now, incidentally, you actually have some examples of carbide complexes, beautiful examples of this type. Just with a naked carbon atom. Something like that. It exists. All right. But I just wanted to show you this nice example because I think it shows what's possible with clusters. And again, this is something very interesting because there's something, and this is one of the reasons why people were particularly interested in the 1960s and 70s and 80s, I guess, in studying these clusters, because if you look at this, again, like I just said, if you look at this, this is starting to resemble the structure of elemental palladium. So if you're doing surface chemistry and you want to understand it, right, you want to understand surface phenomena, one way of doing it is to use clusters. Because these are entities, for example, that can be dissolved. They're molecular entities. And then you can use all sorts of spectroscopic techniques like NMR and mass spec and infrared to potentially elucidate structural phenomena using well-defined molecular entities. That's the point here. And this is an example of that as well, because you have a ruthenium carbide cluster, and these carbide compounds are important in certain surface processes, for example, Fischer-Tropsch catalysis. So people were really looking into this and trying to do chemistry, surface chemistry, with these clusters. Unfortunately, it didn't really work out, right? The clusters tend to be rather unreactive. I mean, they do stuff. You can get them to do some chemistry, but it doesn't really resemble the chemistry of the surfaces. So it's something different. So the whole idea in the 1960s and 70s sort of didn't pan out. That's sort of my opinion, but yeah. All right, now let's talk about how we can actually start understanding the structure of these clusters. Now, we've discussed the 18 valence electron rule. And what we're doing here is we're extending the 18 valence electron rule to clusters. Okay? So instead of calling it the 18 valence electron rule, we call it the effective atomic number rule. What is this rule? It's very simple. It is a way that we can keep accounting of the number of electrons, essentially, in a cluster by taking into consideration the metals, their identity, and the ligands. And it's very simple. We just basically add everything up, and we get the so-called effective atomic number. In German, it's called the magische Zahl, which means the magic number. And yeah, I think that's quite cute. But anyway, if we were to perform an EAN count, an effective atomic number rule count, for molybdenum hexacarbonyl. Now you can think of molybdenum hexacarbonyl as what? A mononuclear cluster, right? So if you look at this formula here, N is the nuclearity and Y is the number of metal-metal bonds. What would the effective atomic number of molybdenum hexacarbonyl be? 18. Yes, yes. So effectively, you can see by looking at that example that it is kind of an extension of the 18 valence electron rule to clusters. Now let's have a look at some examples. We've looked at this a moment ago, this rhodium-4 CO12 compound. Now it's very simple to do the EAN count. You simply count covalently. So for example, we have four rhodium atoms in the cluster. Rhodium is D9, so 9 times 4 is 36. We have 12 carbonyls, it's 24. You add them up, you get 60. So this cluster has a magische Zahl, or an effective atomic number, of 60 electrons. And that's great because we can employ this formula then to determine what? The number of metal-metal bonds. So in other words, if you, for example, a scientist, and you make some cluster and you determine the empirical formula, RH4CO12, just from counting the ligands and doing an electron count, a covalent electron count, you can actually infer the number of metal-metal bonds. That's very useful. Because if you can infer the number of metal-metal bonds, you can sort of start thinking about the potential structure of the thing. So if we, and that's what we're doing here. We have 60 electrons. We solve for Y, we get 6. So now, I mean, that's the structure. We know that that's the structure. But if we didn't know that that was the structure, it's okay. We have to build up a cluster with 4 ruthenium atoms and 6 metal-metal bonds. How do we do that? Well, it's a tetrahedron, as we see here. But that's sort of what you would do. So we've got it's a tetranuclear cluster. We've just determined from the EAN rule that we have 6 metal-metal bonds. So it seems reasonable that at least the core of the cluster will look something like this. Now, this is of course very limited because it doesn't tell you anything about where the carbonyls are going, whether the carbonyls are bridging or not bridging. You can't infer that. But what you can infer is the number of metal bonds. I mean, it would be tempting, since we've got 12 carbonyls, to just do this. But of course, structural elucidation has shown that this compound, in fact, has several bridging carbonyls. But you can see that the core, which is tetrahedral with 6 metal-metal bonds, can be inferred from the EA envelope. This is another example. Again, OS3CO12. We have 3 osmium centers. We can play the same game, and you can do an electron count. Osmium is group 8. There's 3 osmium centers, so the nuclearity is 3. 3 times 8 is 24. We have 12 carbonyls, 24, 48. So, the effective atomic number for this cluster is 48. The Margish-Zahl for this cluster is 48. You can use whichever term you like. Personally, I prefer Margish-Zahl. EAN is a little bit boring. But anyway, it's a 48 electron cluster, and if you solve for Y, you get 3 metal-metal bonds. That seems reasonable, because we've got a nuclearity of 3. There's the 3 metal-metal bonds. And you can do this with all sorts of clusters, right? Another example would be something, in fact, let's do this together. Let's do this together. Because this is important. Rhenium, a rhenium cluster, rhenium H4CO12. Rhenium. That's a rhenium cluster which has, in fact, 4 hydrides. So, let's count the electrons. How do we proceed? You are drinking last night, weren't you?
Yes, way too much.
well, I'm impressed that you made it. Okay, so how do we proceed?
Yeah, there's 4 rhenium atoms, so, and the oxidation state of that thing is 0, so you have, what group was it again?
Rhenium is in group what? 7. Group 7.
So 5 d electrons.
No, you can't covalently. You can't covalently. So
7, 11.
7 times 4. Oh, sorry. 7 times 4 is 28. We have 4 rhenium atoms. Rhenium is in group 7. We count covalently, so it's 28. Does everyone agree with that?
Absolutely.
All right, good. All right, now carbonyls. How do we proceed with that? Yes, 12, we have 12 of them, so it's 12 times 2 is also 28. And what do we do the H?
24.
Sorry. It's early in the morning for me too. All right, now what about the H's? So we're going to have a total of? 4. 4, let's see if I can get that. 4 times 1 is 4. Okay, now count the number. Now we're going to count all of that up.
56.
We get 56. 56. So, now tell me, what does that infer about the number of metal-metal bonds?
So 56 equals 7 times 4 minus 2y.
Not 7 times 7
No,
times
it's
4. N in this case is, what is N? 4, yes, because we only look at the heavy atoms. We have 4 rhenium atoms. In fact, let's write that down. Let's see if I can do it. So, it's 18, so it's 56 equals 18 times 4 minus 2y. And now we can solve for y. What is y? It's 8. Does everyone agree with me? See, I can still do simple algebra.
So it means that all the rhenium atoms have double bonds?
Yes, yes.
So the double bonds count for protons?
Yes. You see, we're now confronted with a situation where, according to our EAN rule, we have 8 metal-metal bonds. How is that possible with only 4 rhenium atoms? Well, the only possibility is that we have something like this. So let's draw our core. These are the rhenium atoms. According to the predictions of this rule, it means so that there we've got 6 bonds. We need another 2. So one possibility would be that you have something like this. So that you have rhenium double bonds. Yes.
How do you know that the nuclearity is going to be 4 and not that it's going to be like 2 times 2, for example?
2 times 2, what do
Like,
you
I mean,
mean?
how do you know that the 4 rhenium atoms are like connected together?
Well, that's a very good question. That's a very good question, Nicole. And as a matter of fact, you don't. And we're going to get to that in a moment. This is highly limited, this rule. It's highly limited and it's oversimplified. You can't make these predictions very accurately. I mean, this rule works like the 18 valence electron rule. It also breaks down, and there's all sorts of exceptions. And if you look at the structure of this compound, it certainly doesn't look like that. But this is what you get from the prediction of the EAN rule, right? That's an important point. So this is about predictions, and of course, Mother Nature doesn't like to be told how to behave according to a simple, stupid little formula like that. But for lower clusters, for OS3CO12, for homonuclear carbonyl clusters of low nuclearity, it works reasonably well. But it breaks down in the face of having weird ligands, and it also breaks down when you get to higher order clusters of nuclearity 5, 6, 7, it stops working as well. And the reason for that is that the bonding is no longer localized between the 2 metal atoms, but it starts smearing out over the molecule, and you can no longer use this rule. So let's just write that down. So, the EAN rule works for lower order, low nuclearity clusters. It starts to fail. For higher order clusters. For higher order clusters, n greater than 5. So when we get to a cluster like OS6CO18, chances are the rule is not going to work. Okay? So it's restricted. It's restricted, but yeah, there you have it. So we need something better, right? We need something better, because this is just not how we want to leave things. And there is something better. There's something much better. And it's called isolobal theory. Now this is the guy that invented this. His name's Roald Hoffman from Cornell University. He won the Nobel Prize in 1981. And at his Nobel Prize lecture, he introduced this new concept, this innovative concept that he came up with called isolobal theory. He didn't win the Nobel Prize for isolobal theory. He won the Nobel Prize for his involvement in the Woodward-Hoffman rules in organic chemistry, involving symmetries and stuff like that. I don't know if you've done that. But anyway, at his Nobel Prize lecture, he didn't talk about that. He spoke about isolobal theory. This guy, incidentally, is quite a controversial figure in chemistry, because a professor at Harvard University named Elias J. Corey also won a Nobel Prize for organic chemistry, for retrosynthesis, accused him of stealing his idea, for which he won a Nobel Prize. So there's a very interesting article in the Journal of the American Chemical Society about this. He denies it. Sometimes scientists can get very catty, right? Because of course Corey didn't win one Nobel Prize, he wanted 2. So anyway, he came up with isolobal theory, and the whole point of this theory is building a bridge between organic and inorganic chemistry. And since coming up with this theory, this classical division between the two has sort of dissolved away. Now, what is isolobal theory? Well, what Roald Hoffmann said is, let's forget about whether it's a metal or whether it's carbon. Let's forget about the identity of the atom, and let's look at the frontier orbitals in the molecular orbital diagram of molecules, species, fragments, and it doesn't matter what they look like. And he said, two fragments, two molecules, two chemical species should behave in a similar way chemically, if they have, in other words, they should be isolobal if they fulfill these three requirements. That their frontier orbitals have similar energies, that their frontier molecular orbitals have the same symmetry. In other words, the HOMO and the LUMO of two fragments that we are comparing can be said to be isolobal, in other words, chemically similar, if they fulfill these requirements. If they have the same symmetry, similar energies, and the same number of electrons in the HOMO orbital, the highest energy occupied molecular orbital. And that's what he said. That's what he said. And this is now a theory that I think people use widely, and this is what I want to now sort of look at. So what he did was, he said, okay, let's take a metal atom in a complex. Well, we've seen this before. In fact, we saw this last week, remember? We have these 9 orbitals on the metal, 5d, 1s, 3p, and we can basically just sort of think of this, if you will, as having these 3 orbitals here, which are T2g, which we know from crystal field theory, which are non-bonding, and we just put all the others together, and let's just hybridize them, D2sp3 hybrid orbitals. There they are. So that's all we've done. We've just basically taken the S, 3p, and 2d, and performed a D2sp3 hybridization. Okay. And we've just left these 3 T2g orbitals non-bonding. So that's an important point, because we're going to now build up molecular orbital diagrams for a series of fragments, and I'm going to prove to you that they're isolobal, in other words, chemically similar, following these 3 criteria from this guy. Okay. So, let's start with methane. Simple. Methane has 4 sp3 hybridized lobes, orbitals on the carbon atom. We all know it's sp3 hybridized. It has 4 hydrogen atoms. So do you agree with me that that's a reasonable molecular orbital diagram for methane? We have simply 4 of these sigma bonds. These are all degenerate. These are degenerate, although I draw the lines like that, they're degenerate. And that's the electron configuration. So you can see it's perfectly stable. That's the, of course, now the HOMO, that's the LUMO. Do you all agree? Highest energy occupied molecular orbital, HOMO, lowest energy unoccupied molecular orbital, LUMO. Now, look at that. That is the molecular orbital diagram of an octahedral complex. There it is. Very simple. We take this hybridization trick I just showed you. This is the metal. These are the ligands. Now, we're simplifying things here. We only consider the ligands to have sigma donation. You should all be familiar with this because we actually had a task on this at the beginning for the 18 valence electron rule. So anyway, this is the molecular orbital diagram that you get. And if you populate, so you basically have 6 sigma star, and these 3 non-bonding orbitals over here. Now, let me ask you a question. Does that fulfill these 3 rules of Roald Hoffmann for isolability? Yes, it does.
We don't know about the energy, right?
Sorry?
We don't really know about the energy.
You don't know about the energy, you're right, but they have to be more or less the same. Now, I mean, that sounds very floppy, I know. But, yes, you're right. It's difficult to assess the energy. Absolutely. But it turns out that if you compare these two fragments, the energies of the frontier orbitals are comparable. Comparable, not the same, but they can be compared. Now let's look at the other criteria. The other criteria was symmetry, the symmetry of the frontier orbitals. Well, it's the same. The LUMO here is a sigma star orbital in both cases, so that fits. And the HOMO here has a similar symmetry and a similar electron occupancy. We've got 2 electrons there and 2 electrons there. It fulfills the requirements of Hoffman's isolobal theory, and therefore we say that these 2 fragments, or these 2 molecules, are isolobal. And the way that we write that is like this. We write it with this double-headed arrow with a little ball at the bottom here. Well, it's actually like a teardrop. It looks like a teardrop. That is how we say 2 fragments are isolobal. So methane, we've just proven using molecular orbital diagrams and considerations clearly is isolobal to D6ML6. So this is D6ML6. That's important. It's not any octahedral complex, right? 6 d electrons, and that's important. So CH4 is isolobal to D6ML6. Let me just write that here. D6ML6, because if it's D7ML6, it's no longer going to be isolobal. If it's D7ML6, we're going to have an electron sitting there, right? And then it's not going to be isolobal at all. You see how this works. Now let's go to the next example. Let's consider a methyl radical, CH3. So that's a CH3 dot. It's if you basically take ethane and you homolytically beam it, you have a methyl radical. Do you agree with me that this is a reasonable molecular orbital diagram of a methyl radical? Again, you have 4 sp3 hybridized carbons. This time you only have three hydrogens, and that means you're going to have 3 sigma bonds, and 3 sigma star. And what is going to be left? What's left?
The radical.
Sorry?
The radical?
Yes. Well, exactly. What's left, actually, if you think about it, is you've got 4 orbitals here and only 3 here. So these 3 form a sigma bond with these 3. Those are shown at the bottom there with associated sigma star antibonding orbitals. And what we're left with is we've got one sp3 hybridized orbital here that is, well, it's not doing anything, so it becomes essentially, if you will, non-bonding. You see that? Now, let's consider a fragment, a transition metal fragment, which is D7ML5. So what do I have here? I have a pentacoordinate metal with 70 electrons. And we build up the molecular orbital diagram in exactly the same way as I did here, except now we only have 5 ligands. 1, 2, 3, 4, 5, each with 2 electrons. The electron distribution of the orbitals on the metal is exactly the same. Still has the same number of orbitals. And instead now we have 70 electrons. There they are, 2, 4, 6, 7. Each red dot is an electron. So we've got 70 electrons and we've got 5 ligands. That means we've got 10 ligands, or 10 electrons coming from the ligands. There they are, 2, 4, 6, 8, 10. So in total we've got how many electrons to play with? 17. 17. And we just put them in, there they are. There's 10, there's 6, and you know what we're left with? We're left with that. Do you see that? So now let me ask you the question. Are these 2 fragments isolobal? Yes. First of all, we have, think about this, the HOMO orbital here is an sp3 hybridized orbital. The HOMO orbital here is a D2 sp3 hybridized orbital, but it has the same symmetry. It has sigma symmetry. Because a D2sp3 orbital is going to form a sigma bond. It's not going to form a pi bond. It can't form a pi bond. They're both sigma symmetric. First criteria fulfilled. What is the second criteria?
Similar energies.
Similar energies, okay, again, that's difficult to assess, but if you look at the, and in fact we will do that in a moment, if you look at the energies, they're quite similar, they're comparable. They don't have to be the same, but comparable. What else? Yes, the HOMO here is 1, the HOMO here is 1. The LUMO here is sigma star, the LUMO here is sigma star. So the frontier orbitals are similar. The conclusion is therefore what? Yes. A methyl radical is isolable to D7ML3. Do you see a pattern starting to emerge? CH4 is isolable to D6ML5. CH3 dots is isolable to D7ML5. Sorry. CH4 is isolable to D6ML6. CH3 is isolable to D7ML5. Is the pattern emerging? Yes. So predict, what will a CH2 be isolable with?
D8ML4.
Correct. What will CH be isolable with? Yes, exactly. So we'll do that in a moment. I just want to show you this. This is to prove to you what's going on here. So what we've got here is an electron density contour plot, if you will, of this methyl radical. This is actually from Roald Hoffman's lecture. And that's what it looks like on the right. And on the left, we have the electron density plot of this manganese pentahydride. This is just a model, right? This is not all being generated by a computer program. MnH5.5 minus. That is, if you do the electron count, a D7ML5 fragment, right? Because it's got a 5 minus charge. And each hydride is a -1. Now look at that. That's pretty convincing, right? You can visually see the similarities. So, that is what isolobal theory is all about. Now what this means is if these two fragments are isolobal, it means they have similar reactivity. It means that a methyl radical is going to behave, according to the predictions, in a similar way, chemically, to a D7ML5 fragment. It means, translated, a species like manganese pentacarbonyl. Manganese pentacarbonyl, which is D7ML5, it's a fragment, will exhibit a similar chemical reactivity to a methyl radical. How cool is that? You're taking a metal complex and you're relating its chemistry and reactivity to a simple organic molecule. And the prediction holds. Very often, it doesn't always work, but it's a theory that enjoys a lot of success and has a lot of predicting power. All right, let's play the movie forward. Here we have now CH2. We play the same game. So here now we've only got, let's look at the left. We've got 2 s orbitals because we've only got 2 ligands because it's a CH2 fragment. What is a CH2 fragment? What's the problem, Julia? Oh yes, what is a SOMO?
Single occupied molecular orbital.
Correct. So this is a SOMO. SOMO is the HOMO. SOMO, singly occupied molecular orbital. Alright. SOMO, that's a new term. It's essentially a HOMO that only has 1 electron. Now, right, so what do we have here? We have 2, so we can have 2 sigma bonds, 2 sigma star bonds, and what are we left with? 2 what? 2 degenerate SOMOs. They have the same energy. Remember, these are degenerates. Now that's going to be isolobal with D8ML4, and you can build this molecular orbital diagram up in the same way as we did before, except you now only have 4 ligands, not 5, not 6. Put in the electrons, put in 8 electrons from the metal, so there we've got 8, plus 2, 4, 6, 8 is 16. Distribute the electrons and you will end up with something like this. Now, here's the question. Are these two fragments isolable according to the criteria? Well, the answer is obviously yes. But why? Can someone explain?
We have similar symmetries.
Yes, we have a sp3 and we have a what?
D2
D2sp3, so it's sigma symmetric. What else? The energies are comparable, okay, take my word for it. What else? Occupancy is the same. We've got two SOMOs, each with one electron, one electron, one electron, one electron, one electron. What else?
Don't you look at like the sigma and DTG?
Sorry?
Don't you look at the sigma and DTG, or do you only look at the HOMO?
You only look at the frontier orbitals. Frontier orbitals are the HOMO and the LUMO in isolobal theory. You don't consider anything that's going on at the bottom there, because why? Why don't we consider that? Why is that not important?
It's fully occupied.
Well, it's fully occupied, but why else? More philosophically? Huh?
It's not relevant for that.
Exactly, it doesn't matter. In chemistry is a subject which depends on what's happening at the frontier orbitals. It doesn't matter what's happening down there. This is totally unimportant. This is unimportant. This is important. This is important. These are the frontier orbitals that are going to dictate the reactivity of the thing. Now, let's play the same game. Oh yes, by the way, what is this thing here?
Carbine.
Yes, it's an apparent carbene. So what are we doing? We're saying, think about this, we're saying that a parent carbene is going to have similar reactivity to iron tetracarbonyl. Think about that for a moment. In fact, let's think about that for a moment. What this means. What does this mean? What this means, and I think it's quite a powerful idea, is that CH2 is isolobal to D8ML4, and that means, philosophically, if you will, that a carbene is going to have similar reactivity to something like iron tetracarbonyl, because iron tetracarbonyl is D8ML4. It means, moreover, that, think about this, it means that ethylene, which is, after all, composed of two carbenes fused together, is going to be isolobal to what molecule?
To dinuclear cluster.
Yes.
But does it also mean that we could put FeCO4 instead of a carbene fragment?
Yes. 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 These are all isolobal. So FeCO4, okay, let me just redraw that. This is then isolobal with CO4 Fe11CH2. They're all isolobal. And it's not just iron tetracarbonyl, you can think of other fragments like iron PMe3, PPH3, 4. That's isolobal with all of these, all sorts of things. So and if you're a scientist, you can turn to isolobal theory if you want to make a molecule and figure out if it's going to be stable or not, using isolobal theory and predict its reactivity. So this is not just learning reactions at all. This is looking at the electronic structure, and I think that's pretty cool. All right, so this is the next isolobal relationship that's important. This is the final one. So here we've got a CH fragment. What is that? It's a carbine. It's a carbine. It's a carbine. You see, we've come a long way in this course, right? Think about it. Think about how much we've done in this very short period of time. All right, that's a carbine fragment. We build up the molecular orbital diagram in the same way. But now we only have one H. So we're going to have 1 sigma and 1 sigma star. We're going to have 3 degenerate SOMOs. 3, boom, 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 each with 1 electron. Now, this is going to be isolable to D9ML3, and there's the proof. So there I've built up the molecular orbital diagram in the same way as we did before, and you end up with 3 electrons sitting there in 3 degenerate SOMOs. Are these 2 fragments isolable according to Hoffman's, Roald-Hoffman's rules, if you will, of isolability? Yes or no? Well, forget the energy, but look at the other criteria.
To have a question, does the fact that one has 3 degenerate LUMO and one is only 1 make a difference?
Oh yes, that's a very good question. That's a very good question. Well, actually that is the LUMO, that is the LUMO, and that is the LUMO. Remember, it doesn't matter what happens above or below.
Yeah, but they're degenerate, right? So technically you have like 3 degenerate LUMOs.
You have 3 degenerate LUMOs, okay, you're right, but the important thing is that, well, what you can think of that is, okay, you have 3 degenerate LUMOs, but at least one of them is required for similarity.
Like, so it doesn't make a difference. So
No, I mean the way to think about this, the way I think about this is look here and look at look at just the first line there and see if it's the same, even though they're degenerate. Even though they're degenerate. All right, good point. But what is important, Nicole, is that we have the same number here, right?
Yeah.
That's important. Right, that's a very good point. All right, so do you agree with me? Okay, so are these 2 fragments isolable, yes or no?
Yes.
Yes. We've got the same number of HOMOs, they're all singly occupied, simply degenerate, 1 electron in each, and the frontier orbitals look the same, they have the same symmetry, etc. So they are isolable. Now, this is to summarize these 3 very, very important isolable relationships we've just derived from first principles from molecular orbital theory, right? And you can do it yourself. You can do it on a piece of paper, right? In a restaurant, or in a cocktail bar. It's not going to find out where you guys go out drinking and hunt you down at 3 o'clock in the morning and ask you to derive these isolable relationships before the exam. Now I can ask you to do that right now because.
What closes the 2, don't worry.
All right. So this is what we've derived. CH3 is isolable to D7ML5. This is an example. So manganese pentacarbonyl is a radical. It is in fact, what is manganese pentacarbonyl? What is it? It is half of dimanganese Mn2CO10, the first cluster we looked at of nuclearity 2. And there's iron tetracarbonyl, cobalt. Now again, just pause philosophically for a moment and consider the implications of this. We have just shown that methine, that's methine, or sorry, carbine, parent carbine is isolable to D9ML3. An example of D9ML3 is cobalt tricarbonyl. That's D9ML3. What does that mean? It means that a carbide fragment is going to, according to the predictions of isolable theory, behave chemically similarly to, cobalt tricarbonyl. How cool is that? What it also means, according to the theory of according to this theory, is that CH is isolable to D9ML3, which is something like cobalt tricarbonyl, which we've just derived. Okay, and that means actually that ethine, so acetylene, is isolable with which metal compound? Cobalt tricarbonyl, cobalt tricarbonyl. It means that these 2 molecules are isolable. So you see how this works. And again, you can interchange 9ml3 fragment for a combine, and you can play all these games. And what you can actually do is take a big molecule and deconstruct it into fragments, which is what we're going to do in the next lecture, and look at those fragments, and you arrive at something really astonishing. Okay, now, I'm going to skip over this. This is, I think, a little bit too advanced. I'll just mention it. This is another isolobal relationship. Basically, if you just pluck off two ligands, you end up with them having the same electronic structure. So the, D7ML5 is isolobal to D7ML3, is isolobal to D7ML1. So if you pluck off two ligands, you end up with the same thing. So D8ML4 is isolobal with D8ML2. And so on. All right. Anyway, and this basically just shows you how that works. You can basically imagine taking these ligands away to infinity, the energies change, and you end up with isolobal fragments. Anyway, that's just a Erweiterung, as we would say in German. Now, let's summarize this. Right. Now, don't worry, this is going to be posted. So we've derived three important relationships. CH3 is isolobal with D7ML5. CH2 is isolobal with DHML4. We've derived that. CH is isolobal with D9ML3. We've also shown that CH4 is isolobal with what? Yes. So there's a pattern. But basically, what we've done here is we just sort of these are some other useful isolobal relationships. Now, I just put it here because I don't expect you to memorize this. For God's sake, don't do that. What is important is just I expect you to know those three isolobal relationships that we derive, and only those three. This is just to show you that you can derive all sorts of other isolobal relationships as well, which is very useful if you're working with a molecule and you want to try and understand it, which we're going to do in the next lecture. Now, why is this important? Well, like I just said, if you're a scientist and you want to make a molecule, you can say, well, with what is that isolobal? It's isolobal with that, okay, maybe it will be stable. You can also predict the reactivity of it. Now, if this was a master's level course, I would go into that. I did in Berlin when I was teaching this at master's level. We looked at some examples where you can take clusters and do reactions with them and predict the outcome using isolobal theory. It's not important, but it's a useful tool not only to predict structure and stability, but also reactivity. Right? Did everyone get that? And the other thing to realize is it doesn't always work. Right? It's a model. It doesn't work. For example, this molecule here, this di-ion compound that we theorized should be isolobal with ethylene, which is very stable. This compound is unstable. So it has its limitations. But it's certainly better than this Mickey Mouse effective atomic number rule thing we have, right? Okay. Now I want to just end off by showing you some examples, some very cool examples of molecules that are isolobal. Well, as I said, it's not just fragments that are isolobal, but if you put fragments together, you can figure out that whole molecules are isolobal. That's cool. So, cyclopropane is in fact isolobal to OH3CO12. How cool is that? What does it mean? It means cyclopropane as a whole is going to have probably the same or similar reactivity, potentially, to this thing here. It also means cyclopropane is very stable. So if you're a chemist, a transition metal chemist that wants to make this, and you see, it's isolobal, what is the conclusion? I can make it, it should be stable. It might be stable. It's at least an indicator that it might be stable. All right. This one we've actually seen. You can now think of methane in a new way. Methane is actually isolobal to a complex. Okay, now look at that molecule. That's a crazy molecule, right? This is a molecule. This was the days in Germany when people used to get money just to make molecules and publish them.
What happened to those times?
This was, I think, in the 80s. The 80s was really a good time for chemistry. The money was flowing, people were just having fun. People were coming to work with hangovers, you know? Those days are over. All right, so we have chromium CP tricarbonyl bound to arsenic, bound to a chromium CP dicarbonyl, so you see the picture. That's the compound. And if you don't believe me, there's the structure. So it's been elucidated by X-ray structure. Look at this. So it's a multi-metallic compound with arsenic carbons. Now don't ask me what this is good for, right? This is, I saw the paper, and it's very funny to read these papers from the 70s and 80s because people were just making compounds. You know, saying, we decided to make this compound because it's interesting. Look, it has an iron, arsenic, cobalt, and it forms a chain. You know? Anyway. Now, if you do an analysis and you break this thing down into fragments, I'm not going to do that, but it turns out this molecule is isolobal with heptane. So, you have this crazy molecule with all these metals, arsenic, chromium, cobalt, iron, and it's, after all, if you do an isolobal analysis, isolobal simply with heptane, and that's the reason. So you can break it down into fragments. This thing is composed of all these fragments here, and if you do this isolobal analysis, you can basically show that it's isolobal to heptane, right? Which they didn't do in the paper. But yeah, if you want to read this paper, yeah, it's 1981, Farnham, Journal of Organic Metallic Chemistry. We decided to make an iron, arsenic, cobalt, chromium, polynuclear compound for fun. Here is the structure. All right, so I think that's all for now. The next lecture we're going to move on and use these isolobal theories, or these isolobal relationships that we've just derived ourselves to do some beautiful, beautiful analysis of compounds. And I'm going to show you how you can think of molecules in a completely different light. This is going to blow your mind.